Now we're recording. Go ahead, Tina.
Okay, so I'm delighted to introduce Dr. Anthony Yacovone. And now Anthony is, well, he was an undergraduate at UMass, and then he did his graduate studies in developmental psychology and psycholinguistics with Jesse Snedeker at Harvard. And I was very fortunate that he also was my postdoc recently at Tufts and MGH, where he did some sort of really interesting work on a bunch of different projects. And now he is an assistant professor at Boston University. And what I love about Anthony is that he's definitely a developmental psycholinguist. I sort of think of him as like that, but he's got one of those perspectives that kind of goes across many, many different facets of cognitive science. So he has a very strong linguistics background, psycholinguistics, of course. He's worked in tracking while reading. Um, and he's worked with ERPs, and as part of his PhD, and also some degree with my group, he's really sort of pioneered a way of embedding psycholinguistic experimental paradigms within very naturalistic contexts, which allows us to sort of connect some of the neural mechanisms of language processing to language processing in the wild. And I'm sure he'll tell you more about that. Anthony, the reason why I thought that Anthony would be a really great speaker for this series, well, not just me, a few of us, is that even though he's not primarily a schizophrenia researcher, his perspective on looking at different populations, and especially his neurodevelopmental perspective, I think would be very valuable. But also, he has been generous enough to share his famous story time paradigm, that story about the turtle, for which a bunch of people in the discourse, a bunch of people in a recent grant that many of us are participating in are using that as yeah, as a way of collecting MEG data and connecting that to various psycholinguistic and computational measures of natural language comprehension. And so, Anthony's also a delightful person and a great collaborator. It was really generous of him to sort of share that paradigm. And yeah, think it will really pay off. And without any further ado, I'll hand it over to Anthony.
Wonderful. Thank you so much, Gina. And likewise, you're also a delight to work with. So I'm very fortunate to spend some time with you in your lab and get to stay in Boston area. So let me just share my screen and we'll get going. Okay. Okay, can everybody see my screen and everything's good? All right, great. So yeah, thank you so much for the invitation. I am delighted to be here. And I think my work is very relevant to everything that people think about in this group. But as Gina said, I have a developmental background. So I'll be presenting some work from some of the kid studies that I'm going to be writing up and sort of hopefully getting out there soon. So the topic of this talk is telling the whole story, insights from naturalistic language research across populations. So I always like to start with just sort of appreciating how rich and complex natural language comprehension is, right? It happens in these sort of wild environments. There are multiple participants, your friends, you might have your own idiosyncratic language. You might be engaging with language in multiple modalities, right? Both reading and talking about the same thing. And you might even be experiencing language in multiple modalities, such as sign language or bilingual environments where multiple people are speaking or producing language in distinct ways. So why might we want to try and study language in these natural contexts? So natural language is undoubtedly, Their environments are very complex, highly variable, and fast-paced. Yet they scaffold language comprehension in a lot of critical ways. So, in psycholinguistics, we have a tradition of studying language using sort of single isolated sentences or slower than natural presentations, sort of abstracting away from the rich environments in which language occurs and presenting them with minimal extra-linguistic contexts, and sort of creating these tightly controlled experiments and designs, and having certain tasks to make sure that we're engaging with language in a particular way that's relevant to our research questions. So, why might we want to use ecologically valid methods? I'm going to try and say that it's more than just characterizing what natural language comprehension is, right? And it's actually about the ways in which natural environments provide richer cues to the comprehender. And they also are better environments to help people or populations demonstrate their linguistic abilities in ways that sort of, might not be as apparent in certain cognitive tasks. So in this talk, I'm going to use something called linguistic prediction as a case study. And this is because prediction has been sort of argued to be foundational to language comprehension in adults. And there are sort of many populations that are thought to be weaker predictors or have weaker prediction skills. And so I want to test whether or not this is true when we study these populations in sort of the most optimal environments that we can. So I will begin to address some of these points in 2 plus some bonus work in progress studies at the end. Great, let's jump right in. I'm also happy to take questions as I go. Please interrupt as you feel. So here's the outline of my talk. I'm going to start by motivating my questions and my methods. Gina mentioned the storytime paradigm, and this is a naturalistic comprehension task that I'll get into more details soon. I've selected some experiments that use the storytime paradigm to sort of illustrate the points that I hope to make about studying language in natural contexts. The first one is prediction of phonological forms in English-speaking adults. Then I extend this to testing the same phenomena in English-speaking children around 4 to 5 years old. And then I want to demonstrate a different version of the storytime paradigm, which is more correlational, which might be more familiar to a lot of people in this group, those that have been doing other types of natural language studies. But these are all works in progress. So I'll present interpretations, but some of data collection is still going. Then I'll end with my final remarks and Q&A session. Okay, so I just want to start with some basics of adult language comprehension. So we can think of the language system as a network of linked representations, sort of linking linguistic forms with higher level meanings. And during comprehension, linguistic input initially activates low-level representations of forms, and this can sort of be represented in a hierarchical way. So the incoming speech will activate the sounds of my language, and then I can use this information to start building up higher-level, more abstract representations of the language. So I can turn sounds into phonemes, words. Those words can become semantic meanings or syntactic structures. And this will all sort of lead up to the highest level representation of our world knowledge, or sort of the event that we're trying to understand from an utterance. Now, at the same time that information is flowing from the bottom to the top of this hierarchy, information can also flow back down. So, information from world knowledge can constrain how we're thinking about a sentence structure. That the sentence can sort of help us understand words. Words can help us understand ambiguous sounds, and so on. And this process of information flowing from a higher level to a lower one is often called top-down processing. Now, for this talk, I'm going to just say that prediction is a type of top-down processing, where something becomes activated from the higher level to the lower level before it actually appears in our input. So let's make this a concrete example. Imagine I say, I like my coffee with cream and. This sentence context is being represented as the sounds, the phonemes, the words, sort of bits of meaning like hot, cafe, drink, some type of structure related to the utterance. And then you might, this utterance might conjure up ideas about, a hot coffee mug. There's some milk or some creamer, and then there's something else about to be added to this coffee. And so what you can do is sort of start to activate things like sugar, a spoonful of sugar. And at the same time, this information is going to start moving its way down the hierarchy activating words and their meanings, individual phonemes, and maybe even the acoustic information that you're expecting to hear next, all before sugar is produced. Good so far? Wonderful. Okay, so linguistic prediction. Oh yeah, question, sorry. No, okay, great. So in the system, prediction can occur at multiple levels, right? At higher levels about semantic representations that are likely to come up next, and even at lower ones related to sort of the acoustics or the forms that we might expect to hear. And decades of psycholinguistics have really demonstrated prediction using a variety of methods. So eye tracking while reading, visual world eye tracking, and electroencephalography or EEG. I'm going to focus today on EEG. And what is this method? So essentially you probably are familiar with this method, but we put a cap that's embedded with electrodes onto a participant's head. We sort of attach it to an amplifier so that we can see the sort of micro changes of voltage that are being sort of represented on the scalp surface. And what we can get is a nice time series data of, across the course of an experiment, while you're listening or reading or watching language, we can get the sort of temporal changes in your brain activations across time. We do this over and over for all of our participants, and then we chunk them up into little tiny epics that are related to, let's say, a critical word that we're interested in. And then we average all of these together so that we can get a cleaner system or a cleaner representation of this signal that is sort of reduced in noise. And these can be represented on each electrode. And we get sort of a stable representation that's often called an event-related potential or an ERP. Now, there are some critical ERPs for this body of work that I want to go through. The first is the N400. And during comprehension, the N400 is evoked by all words, even those presented in isolation. So for example, here I'm showing you a typical ERP setup. So we have time on the x-axis. The 0 is the target of a particular word. Negative is plotted up in these plots and the rest of the plots for the presentation, and positive is plotted down. So if, for example, I say psychosis out of the blue, presented in isolation, your brain is going to produce a response that looks something like this. And what we can see is that around 400 milliseconds, there's a negative going change in the ERP waveform, and this is called the N400. And you can kind of think of this ERP as reflecting the relative ease of accessing all of those sound, form features, all of the semantic features that I had outlined in that hierarchy earlier. And so this effect sort of emerges in sort of the central parietal area of the scalp, and it's very robust, across paradigms and across populations. So we also know that the N400 is sensitive to, let's say, prediction, right? So the easier that this process of activating the form and the meaning of words is reflected in sort of a gradient on the N400. Let me demonstrate what I mean by that. So if I said Anthony drank the freshly brewed beer, imagine that was the continuation. And if I asked 10 people what continuation that might be, 1 out of 10 might say beer. And this is often sort of operationalized as a closed probability, right? So 10% of respondents would think that this word beer is coming right after the context that you just saw. Now imagine this is the brain response that you get to beer. If instead I said something like the freshly brewed tea, 3 out of 10 people might think that this continuation is expected. And so it has a closed probability that's a little bit greater, 30% close. The N400 response that we get for tea is sort of reduced somewhat relative to beer. And now coffee, which is probably the continuation most people would say, actually right now I'm drinking both coffee and tea. So this is kind of a tricky example here. But this one had a closed probability of 60%, and the brain response would be even more reduced, right? So the easier it is to access the features because you've anticipated them in advance, the smaller or more reduced this N400 response is going to be. So the N400 is sort of inversely related to the word's predictability given its context, and not just sort of in the sort of categorical way, but in a very continuous way. So we can see this plot here, amplitude is on the y-axis, and closed probability of a particular word given its context is on the x, and you can see that it's inversely correlated which is a very robust and stable finding. So we can also interrogate not just, did prediction happen, but rather what level of representation was prediction occurring at? And we can do this by looking at words that are completely unexpected, that nobody would provide in sort of a sentence completion task, but they have particular properties that are related to the most expected continuation. So if I said nobody knows the time, as this room has no clock, is the expected continuation here. And it has a close probability of about 94% in this particular experiment. Now, I could present something like scarf, which doesn't really share any relationship to clock. And in fact, nobody guessed scarf as a continuation for this sentence. And you can see a very robust N400 effect here. Now imagine I said alarm. Now, no one guessed alarm in a sentence completion task, but it shares a lot of semantic features with the word clock. And so the N400 is actually reduced because the features that are sort of shared by both clock and alarm have been activated in advance, and it's easier to process the word alarm, even though it was completely unexpected. Now, the interesting case comes with the word clerk. Now, this shares no meaning with clock at all. It's not guessed by anybody in a sentence completion task, but it does share sort of its orthography with the word clock, right? And so the question is, if you are predicting sort of the orthographic or phonological or form features of a word, you should see reductions for this word, even though its meaning is nonsensical given the context, right? And what do we find in this study? They show that the red line, which is the N400 response to clerk, is just as reduced as the word alarm, suggesting that comprehenders in this particular environment were able to predict at the lowest levels of the hierarchy in advance of the word appearing in their input. Okay, good so far? Awesome. So you also see that there's sort of this later effect that's emerging in sort of a more positive direction. And this is often called the P600. So P for positive, 600 for 600 milliseconds and beyond after a target has been sort of produced. And I didn't say this before, but the N400 is N for negative going around 400 milliseconds. And you can kind of think of the P600 here as sort of engaging in this process of re-evaluating your input, analyzing or thinking about the error that you just encountered. So was this my mistake? Did I just have a slip of the eye? Sort of what's going on here? Just taking more time to pause before continuing to go on with normal comprehension. And this effect sort of is more posterior, and that's highlighted there in red. So although sort of prior work has shown prediction at the levels of semantics in word form, form-based prediction of this kind, right, getting reductions for clerk relative to clock, seems to be more limited in the sort of literature. It seems to be really influenced by how much time you have available for making your prediction. If things are coming very fast, you're oftentimes not able to activate things all the way down the linguistic hierarchy. And so you might not be able to predict form in those environments. And it seems to be influenced by the predictability of the context. If your context is extremely constraining, very, very predictable, you might have an easier time of activating things across the hierarchy. So now let's sort of take the stimuli from the study that we just looked through, and I'm going to present them at a faster rate, right? This is sort of what they did in the experiment as well. So now you get nobody knows the time as this room has no, and then you get the same sort of continuations. Exact same experiment, exact same experimental method and design, but now things are just coming at you a little bit faster. The pattern is very similar for both the completely unexpected and the semantically related alarm conditions. You do see some type of reduced N400, some facilitated processing of alarm in this context. But now, without, relative to the last condition, you don't see that facilitation happening for the word clerk anymore. Given this fast-paced environment, form-based prediction seems to not be as robust or even occurring given the particular experimental context in which language comprehension was occurring. So we don't see this reduction for clerk anymore, and the P600 is even a little bit smaller as well. So just kind of give a summary of where we've been so far. The N for 100 is sort of this negative going peak around 400 milliseconds. And you can think of it as the ease of accessing all of the features related to the form and the meaning of an input. And it seems to be smaller when that word's sort of semantic or form features have been pre-activated, either accidentally by wanting another continuation, or if that is the target, the best completion, the best continuation of a sentence. And then we saw something like the P600, which is this later emerging ERP component. And we can think of it as sort of reprocessing or reanalysis of sort of this phonological error in the domain of form-based prediction. And it seems to be larger when errors are really sort of clear mistakes, right? So the closer you get to what you wanted, the larger this P600 is. So the literature has really questioned whether form-based prediction is just sort of a lab artifact. Takeaways from the prior work: form prediction only seems to occur when the predictability is extremely high and when the presentation rate is slower than natural, right? And the interpretation was that it just takes longer for us to predict form at the lowest levels of this hierarchy relative to semantic features. And so the logical conclusion is that form-based prediction is probably unlikely to occur in natural language. This is because natural language is, relatively unpredictable. Words have sort of a range from about 10% close probability on average in natural text and corpora. And it unfolds roughly 2 times faster than the language that we're presenting in the lab, right? I seem to be speaking at a particular rate that would probably be slowed down in a typical experiment. And there is some evidence for form-based prediction at faster rates, but these are extremely simple experimental designs that were really designed to promote prediction. They didn't have any unpredictable targets or filler sentences. And so I want to first test, when we look at this phenomenon in natural context using the storytime paradigm, do we see evidence of prediction emerging in adults? Great. So I'm going to focus on form-based prediction. And in study 1, we're going to look at whether or not adults predict the phonological features in spoken language, in spoken English. So this is work that I did during my PhD with my collaborators, Brian Waite, Tanya Lavari, and Jesse Snedeker. And this is sort of the famous turtle story for those that are familiar with the design. So what was the method? So the storytime paradigm, essentially people just watched a 30-minute cartoon that I made of a story book being read aloud. And I sort of spliced in critical manipulations that would allow me to test the hypotheses like those presented in the prior work. So what does splicing mean in this context? I would record the story, take out the target word, and then put in a particular manipulation so that I could maintain the audio on both sides of the critical manipulation. And then we asked a series of open-ended comprehension questions about the story. This is a mystery story about a turtle that gets stolen in a school context. And so, we ask about who stole the turtle, right, to just gauge engagement. The participants for this experiment here were 30 native English-speaking adults. We had a 2x3 design in this naturalistic environment with 180 target words. So we manipulated predictability, whether the word was more expected given the context or less expected. And we had 3 different manipulations. One was the baseline, so the word that was actually presented in the story. And then the other one was changes in its phonological form. And so what we did was, in a predictable context, like these hairs prove you were at the scene of the crime, we would just change that sort of initial vowel and make it a slight deviation from the target and say crame. And then we would make it even further away, a more deviant input, and change the initial onset, so nime. And then we did that for both words that appeared in less predictable contexts. So they are only found in a certain river, rover, or piver in Texas. Now, we didn't want to completely destroy the story, right? Because sentences are building on each other in the storytime paradigm. And so if we had a completely nonsensical continuation, it would sort of break down or degrade the sort of integrity of the story. That's why we went for these slight phonological variations at the onset and sort of the initial vowel. So for predictability values, we had sort of a good range of prediction predictability here. So high close was around 85%. And then it was categorically different for the set of the lower close words. We matched on critical features such as frequency, neighborhood density, and there were about nearly 5,000 words that we looked at, and about 2,000 content words to analyze. And we used a speaking rate that was about 3.25 words per second. So not too slow and not extremely fast. So here's some examples of the stimuli. I hope you can hear them, but I just want to demonstrate what the splicing procedure looks like. So
these letters are so squiggly, I can't even read it. It's called cursive, silly, and the party is this Sunday. That's 5 doors away. I'll ask my mom as soon as I get home, Alex said, pushing on his glasses.
So you can see the target words are sort of highlighted in those colors there. Now this would be another version of the experiment.
These loaders are so squiggly, I can't even read it. It's called cursive, silly, and the party is this Sunday. That's 5 days away. I'll ask my mom as soon as I get home, Alex said, pushing on his glasses.
Okay, great. So you can see there that the sort of experimental designs are being manipulated across each version of the story, so that we can still get the same type of experimental control, but now in this more ecologically valid paradigm. And I'll skip this last one for time. So what were the predictions for this study? So we would expect on the N400 that words in predictable contexts that share sort of, that are more similar to the target, like kek relative to cake, might be showing a reduced N400. So that's this red line here. That's sort of the clock clerk example. We also expect, because these are phonologically deviant and sort of clear mispronunciations, these P600s or late error responses to start to emerge. And then the last prediction is that the baseline, right, the word that is from the story, should also be varying in the N400 size, such that words that are more predictable, more pre-activated in advance, should show smaller N400s relative to those sort of baseline words in less predictable contexts. Okay, so let's take a look and see what we found. On the left is the high close conditions, the predictable conditions, and on the right are the lower close conditions. So what did we find? Sort of exactly in line with our hypothesis here. The more similar violations show reduced N400, but only in contexts where that original word was really predictable. We don't see similar reductions in less predictable contexts. We see P600s emerging for these sort of mispronunciations, and they don't seem to be different between them, suggesting that error processing is still happening for both types of mispronunciations, regardless of how easy they were to originally access. And then our last prediction is also supported, and we see that the N400 for more predictable words is sort of reduced or smaller relative to the baseline words in less predictable environments. I'll just pause here for a second. Good so far? Great. So the conclusions for study 1 is that the N400 was reduced for the same word that's more similar in its phonological form, the onset same condition, in high close but not low close environments. We see P600s emerging to these mispronunciations in natural contexts, right? Suggesting that even in sort of more natural environments where you're sort of listening and watching to a really rich supported context, you're still engaging in some type of reprocessing or thinking through of what you're actually hearing. And we saw that this baseline is also changing across predictability contexts, replicating prior work. So what should you take away? That classic ERP experiments can be run in sort of ecologically valid, really rich discourse environments. And that form-based prediction is occurring in this natural context, despite it being more variable, less predictable on average, and produced at faster rates of presentation. Okay, so I have about how much longer? 10? I want to leave time for questions, but.
Yeah, you have a bit more than 10 minutes.
Okay, so I'll go for 15. Great. So in the second study, I want to test this question of, we demonstrated this sort of robust phenomena of prediction, right, at the lowest levels of the hierarchy in natural contexts. sort of in contrast to what the literature had been saying about predictive abilities in sort of naturalistic environments. And so now I want to use this design to test whether or not the same phenomena are present in a variety of different populations that have been argued to be weaker predictors on average. So this is sort of doing the exact same experiment, but now with a set of 5 and 6-year-olds. So we might expect 5 and 6-year-olds to predict word forms, right? So if we talk to them, it's relatively easy and quite adult-like. Pre-activation of form is theoretically allowed at any age across, development. And in contrast, the data seems to suggest that form-based prediction is sort of necessarily requiring rapid coordination across these levels, efficient processing systems so that information can flow fast enough, knowledge about one's language and the world. And even in my prior work, I've shown that kids are less knowledgeable, unsurprising, relative to adults. They are slower at basic cognitive tasks, and they seem less able to recruit sort of top-down information, stuff that's coming from higher levels of the hierarchy to inform their understanding or interpretation of representations at lower levels. Also, literacy has been argued to play a role in the development of prediction. And so in a recent hypothesis, people have argued that reading is sort of provides optimal conditions for learning how or developing the ability to predict word forms. So it's self-paced and it's painfully slow at the beginning, right? Graphemes are relatively stable, with the exception of fonts changing here and there relative to phonologically produced words. And whole word prediction is sort of helped by this initial decoding process, right? If we're slowly working through a word, we sort of are more in tune with the representations of form. And we see that increased proficiency in reading is often linked to increased prediction of written words in reading studies. And over time, people start to begin to predict spoken words from listening to sort of the language that they're learning to read. And these sort of processes feed each other and help with the development of form-based prediction. So this sort of makes an interesting case, which is that form-based prediction may not be central to language comprehension, but rather a cultural artifact that emerges under sort of specific developmental circumstances, namely being able or learning to read in your language. So what's the evidence for prediction in children? And I'll sort of work through this. I'll skip these right here. This is just a form-based prediction study using eye tracking methods, basically saying that kids will look towards objects that seem semantically expected given a sentence context, but they don't do so using form-based cues like a ice cream cone versus a ball, for example. So in ERP experiments, what can we see? So adults and children will produce N400 effects to semantic anomalies, like the family moved into a new radio that will produce large N400s for both kids and adults. What I'm showing in the left column is the adult N400 data, with the solid line being the semantic anomaly and the dotted line being the congruent condition. And you can see that both kids and adults are showing differences between these conditions in the expected direction and roughly at the same time. Critically, only adults are producing the P600 to these semantic anomalies, posing interesting questions about the ways in which kids are dealing and processing errors. And across development, we see that the N400s, they sort of emerge earlier and become smaller over time. And P600s start to also emerge and they become larger over the course of development. The N400 effect changing could be, possible 2 explanations here. The first is that lexical access is getting easier for kids as they get older, right? The sort of machinery is developing and allowing for more efficient processing. The other sort of less satisfactory answer is that kids' scalps are pretty thick, are getting thicker over development. And so it might be less obvious what the underlying signal is because of these changes in the scalp. But the scalp explanation can explain the changes in the P600, for example, because we see it getting larger. So there seems to be some indication that the process is changing itself. So let's just jump right into study 2, which is to say, we expect kids to be weaker predictors for a variety of reasons across the literature. And I want to know if form-based prediction, when kids are engaged in the sort of rich naturalistic context, will emerge. And so it's the exact same design. Kids watch the same cartoon, which they loved, and they answered comprehension questions. And the data I'm going to show you are from 28 native English speakers from 5 to 6, from 5 to almost 7. Here, just to remind you, are the conditions. To determine predictability for kids, right, we collected a sentence completion task online with the actual target age range, because we can't really make assumptions that if an adult was guessing this word, given the context, are kids also likely to guess these same words, given the exact same materials. So here's just a fun example of how we did the study online. It recently was published, so if you're interested, you can find it in Journal of Child Language. But here's an example of a kid doing the closed task.
Emily sniffed. Because my turtle ran away. On Tuesday, I took Bubbles out to play in my backyard so he could have some fun in the sunshine. I thought he was taking a nap, so I went inside for a drink of water. I guess turtles can move really fast when they want to, because when I came back outside, he was gone.
So in this example, you can kind of see another use of the storytime paradigm, which is to actually have explicit productions happening in sort of these sort of more natural contexts. So you can see that the child emphatically knew that the continuation of the sentence was water, and she was able to provide and demonstrate her prediction skills. Okay, so on average, kids are less likely to predict, was the results of that closed study, but they were very correlated with what adults were producing. So what I'm showing you on the x-axis is adult closed responses for the same target words, and on the y-axis is what kids responded to. And you can see that there is quite a strong correlation, where there seems to be two clusters. Words that were very predictable were both predictable in adults and in kids, and words that were less predictable, kind of in those 0 predictability ranges, were also less predictable for adults and kids, sort of paving the way for using this paradigm to study the 5-year-olds. Okay, so here are our predictions for the adults, right? A reduction in the N for 100 for those clock, clerk, cake, keck examples, but only in predictable contexts. P600s emerging to mispronunciations, even in natural context, natural speech, and it changes in the baseline N for 100s for the words from the story, just based on their natural predictability values. And we sort of replicated that with adults. Now, what do we see with kids? So this is what I'm showing you is the predictable context. We see reductions for that red line, which is sort of the phonologically similar word, right? Clock, clerk, cake, keck, relative to more deviant or phonologically different words here. But interestingly, you can see that this effect is much larger, more prolonged, and there doesn't really seem to be a P600 emerging in that late window like the adults. In lower close conditions, we actually see sort of no facilitation for even 10% predictable words. And you can see that because the black line, the sort of baseline keck, is showing the same size N per 100 as the other sort of violations here. So it really doesn't seem like in these less predictable environments, they were able to pre-activate or predict really anything sort of meaningfully. And that is in contrast to the adults. So that's the N per 100 pattern, lack of P600 pattern. And there is a difference in the baseline, suggesting that prediction is occurring in this population here. Okay, so the conclusions for study 2, the N for 100 reduction for the phonologically similar or onset same errors emerged for both adults and kids in high close but not low close environments. We see P600s for adults but not children, suggesting that adults are engaging with these mispronunciations in different ways than kids are, right? If you sort of think of yourself as a child listening to an adult speak or tell a story, you might be less confident that, maybe sometimes it's pronounced as keck and not cake, right? Maybe I can allow more flexibility in sort of the phonological forms that I'm experiencing because I'm still learning my language, right? And you sort of replicate prior findings about these baseline differences in both populations. So form-based prediction seems to emerge early on in childhood for spoken language. And there seems to be some type of developmental change related to how mispronunciations are handled across development, which I hope to explore pretty soon. Okay, so that's study 2. And now I just kind of want to end by showing some works in progress. So a quick caveat about the children in our population. So we can't really rule out sort of this literacy hypothesis, how reading is going to influence prediction, because the average age reported by our parents in the study, that kids were starting to read at like 4 years old, and these were 5 and 6 year olds. So reading started to happen for our population. Half of the children were reported to have already achieved reading fluency at this age. You know, parents oftentimes like to overinflate their kids' performance, so we can't really tell how literacy is playing a role in their prediction abilities. You know, a point against that was that parents only rated their reading proficiency as being adequate, even though they are really fluent readers. So there seems to be some conflicting information in our population here. So we had 2 options for continuing this work. One is to replicate the study with pre-literate 2 to 3 year olds, and sort of that is work in progress as well. And to try and replicate this experiment in a language that doesn't have a primary written form, like American Sign Language. And that study is now under review, and I can sort of just give you the tagline. People are predicting form, even if they don't have a written language, and they do so in this visual manual modality as well. Okay, so these are all works in progress, but I thought that they would be interesting to this group. And they sort of all use the same paradigm. So it's very easy to sort of work through big chunks of data here. And so this is sort of investigations of different cross sections of populations. And this is work done with my collaborators over at Harvard. So this storytime task, this set of studies here, is correlational. So in contrast to the manipulated version that I just showed you, where I actually go in and insert particular critical experimental designs, now we're just doing a correlational design. So they watch a cartoon, and this cartoon does not have any experimental manipulations at all. And it looks something like this.
That day, she wore her furry pink vest over a green rainbow t-shirt with a jean skirt and blue leggings dotted with pink circles.
So they just sort of watched a basic environment with a single narrator sitting on a couch, and then occasionally she got presented with images from the storybook itself. Now, so what we can do is extract the sort of ERPs evoked by every single word, because there's no longer critical manipulations, but every single word, and characterize particular properties that we might be interested in studying theoretically. So for example, we can pull out the word's predictability given its context, just its frequency in sort of a set of corpora to just see how frequent is this word occurring in everyday life. We can pull out a lot of other nuisance variables, like how long was it produced, its concreteness, its neighborhood density, its location within its sentence, its location within the story, right? Things that we might think influence the processing of this word in this moment. And we can also characterize features of its environment. So for example, if we're studying the word pink, we might also include in our statistical models features of the word that came right before it, as well as features that are coming after it, right? If you think about how fast words are being comprehended, you know, in the second window that we study for any given word, we're also going to be capturing processing of the next word. And so we want to try and control for the environment in this more correlational design. We can also test things like semantic similarity between, you know, adjacent words. And so if we're interested in the word pink, we might characterize its semantic relationship to the word that came right before it, sort of a priming-like study. So I just want to show you some data that pull out the prediction effect. So looking at 3 different tiers of predictability, a less predictable word, a more predictable word, and a really, really highly predictable word, and show you how this changes across development. These kids are all listening to the same turtle snatcher story in this correlational design. For this set of teenagers, there were 30, and they were about 14 to 15 years old. Here's an example of one of them. I'm going to just show you some plots. Here we have time on the x-axis, amplitude on the y, and the target onset is sort of the target collapsed across every single content word in this 30-minute story. I'm showing you sort of averaged around this particular region of the scalp. And what do we see? So for low predictable words, we sort of see a long sort of bump starting around the 300, 400 milliseconds. And we can see that as the words become more predictable on average, there is this reduction in the N per 100. Note that this is sort of a more correlational design. So we're using a lot of every single word, which does introduce some noise and creates sort of this temporal smearing that we're seeing here. So for teenagers, this story was a little bit easy for them, and they didn't really pay attention as much as they thought they did. And so, this sort of reduced ERP pattern here could be a product of both them just being older, which is sort of showing reduced N per hundreds relative to other kids, or sort of less engagement because this is a really childish story for them. So the preteens is kind of our target here. And so this should actually be around 9 years old, and they ranged from 9 to 12, excuse the typo here. And what did we find here? We also replicate that now we see this graded pattern with the red followed by the blue followed by the black, demonstrating prediction is happening for every single word in our story in a very tightly controlled way. So that's 9-year-olds. We did this also with preschoolers. So this is now 5- and 6-year-olds doing the story. Here's an example of one of them. And we start to see less prediction emerging for this age range, right? We do see it sort of start to emerge in the late window after 500 milliseconds, but there is sort of a bunch of noise happening here. One thing that we learned was that kids around this age, they're not being supported by the visual context of watching a cartoon, but rather they're just listening to sort of decontextualized speech. And kids this age actually don't know that there are libraries in elementary schools, or they don't actually know the procedures of actually going to elementary school because they haven't been yet. So their world knowledge is less able to scaffold their understanding. And so prediction starts to break down somewhat in this age range because of the content being produced in the story. Okay, so what did we do? So we decided to go even younger and look at toddlers, but this time we changed the story. So this time we used materials that are going to be really salient to the particular age range. So stuff about Rosie going to a preschool, or a book that's designed for early language comprehension that's pretty redundant and talks about things in sort of everyday life. And so this is work that's in progress. There are 13 3- to 4-year-olds for this paradigm here. You can see one of them participating here. And what do we see? Relative to the 5-year-olds, when the story is contextually appropriate for the age range that you're studying, we start to see prediction emerge such that these 3 predictability conditions are pulling apart in ways that we had predicted. Now you'll note that the prediction window is a bit later for kids. So, we know that kids become more efficient processors over time, and that the N per 100 moves up and gets earlier as we get older. And so this late window is just sort of reflecting the fact that information processing is not as robust or efficient in kids, but in these natural contexts, they still are able to show that they are doing robust forms of prediction. Okay, great. So the last 2 pieces of data that I want to put on the table is a contrast between looking at prediction within autism spectrum disorder. And so the background here is that there are 2 hypotheses on the table about sort of the cognitive profile of autism. And one group sort of argues that the sort of language profile that emerges is due to some global deficit in prediction. And this is also supported by this idea of the weak central coherence theory that says that people with autism sort of prioritize more locally available cues relative to those that are sort of more accessible in the broader or global discourse. And so the question here is, when kids, both neurotypical and kids with ASD, are engaging in naturalistic language comprehension, do we still see the profile of sort of weaker prediction skills in these 2 populations? So what I'm going to show you here is the neurotypical group here. It's still in progress, but what you can see is that relative to the same age range from the preteens, we see the same pattern of findings. So it's the exact same story, exact same sort of design. We see this gradient emerging. Now, the question is what happens when we look at kids with ASD? So this is still about the same size sample, still being collected, about 11 kids, same age range, similar sort of literacy skills measured by, administered tests like the SELF. We also see that kids with ASD are predicting. They show the gradient in same ways as the neurotypical kids. And I just want to put them on top of each other so you can see. That's the neurotypical, and that's the ASD kids. So you can see that the gradient still exists. There is sort of a weaker prediction effect. You can see by the black line, that sort of most predictable line is not as low or reduced. So there seems to be some slight differences, but we're still investigating with a fuller sample to see if this holds. But in general, right, this is demonstrating that kids with ASD are engaging in prediction relative to the same relative degree as their neurotypical peers. And then this is just comparing across the two studies of the same age range, and we can see that the effects are relatively similar. So one group is from that previous study that I showed you, a full sample of 30, and this is sort of the same group. Okay, so my final remarks, and then I'll wrap up. So I am arguing that in order to tell the whole story about how populations are understanding language, we really have to study language abilities and language in these naturalistic contexts. And today I've shown that prediction can occur in highly complex and variable environments. Prediction is robust and present by early childhood, and that populations that we thought to be weak predictors really aren't so when they're sort of engaging in comprehension in the wild. And I sort of hoped to have demonstrated the utility of the storytime paradigm. It allows populations to engage in science, and sort of these tasks are accessible for those that are underserved by our traditional methods. It oftentimes reveals greater performance despite the increased variability. It comes in two fun flavors, right? A manipulated version as well as a more correlational type design. And it really is an opportunity to balance both experimental control, theoretical clarity, and ecologically valid methods. So just a quick thanks to all of my past colleagues in labs, my funders, and thank you for listening. Happy to take your questions.
Well, thank you very much, Anthony. This was a wonderful talk, very engaging. Now we can do some questions. Let's dive into some discussion. So I will ask you to raise your hand if you want to ask anything to Anthony. Okay, Lena, go ahead.
Thank you, Maria. Thank you very much, Anthony. I really enjoyed this. This is excellent. In fact, I was stunned by the fact that close probability predictability exists in children. I never thought that similar predictability scores can be derived. So this is excellent. I had a couple of thoughts on questions actually on the reason why children may have lower predictability. They have better than expected, but still lower than adults in data set. One thing you kind of more or less ruled out is immersion in reading is not necessary condition for predictability to emerge. That's fantastic. But two other things that I was thinking about is the knowledge of structure of language, like syntax or grammar. At the age of 6 and 5, there will be some variations in that compared to adults. And secondly, the time that kids take to process a sentence, the speed of processing. Are these variables critical when you look at the variability among words in children?
Yeah, that's a great question. So, few things. One is that when we do look at the sort of closed probabilities from that sort of sentence production type task, one thing that closed probability is doing is that it's very specific to a single lexical item. So if an adult and a child, like if a child isn't producing the exact word that was written by the author in the storybook, right? Does that mean that they're not predicting, right? So lexical predictability is often underestimating prediction at higher levels of representation. And so what we did was we actually coded children's responses on whether or not they were semantically related, right? If the word was dog, but they decided to say puppy, right, is that indication that they're not predicting to the same degree, right? And so when we look at sort of the responses stratified in these new ways and categorical ways, we show that kids are actually showing even more robust prediction. They're just not using the words that adults wanted them to. And so whether or not we sort of would train them to produce the word from the story or use texts that don't rely on particular idiosyncratic words that an author might want to put in their book, that will sort of be really critical to understanding prediction in the population that you're interested in. Now, the other question is about syntactic variability, experience with language. We know that proficiency definitely does play a role in prediction abilities. So you can look at second language learners and sort of see that their proficiency in the language that they're processing does influence how likely they are to produce the same utterance as someone with higher proficiency. The other thing is that within a language itself, English is pretty structured in particular ways. And so there's kind of we were looking at just nouns. And so the English sets up nouns in particularly salient places. And so you can kind of even guess that a syntactic close probability, right? A syntactic predictability value is even higher than particular words that might come next, right? You expect this to be a noun. You might not know what noun it is. But the work that I was showing in ASL, so sign language has more variability in production and sort of sentence and structures and word orders. And so we did the close task with participants of deaf signers. And what we saw was much more variability in the types of continuations that they're providing, not just necessarily the words, but they would go on to give different clauses, give a noun sometimes, give more constructed actions, right? And so this variability plays a role in how we understand prediction happening in these populations. And so even though their language might not be as conducive to predicting a noun in this particular way, they're still able to engage in prediction despite this variability. But it definitely plays a role in how we sort of see their productions coming online.
Thank you.
Mm-hmm.
Thank you very much for that. Emily, you have a question?
Yes, maybe this is naive. I'm not an ERP person, but like listening to you, it made me wonder, like, because your tasks are like always the same scripts, like people listen to always the same scripts, but like, could we use something like that to like assess like how predictable, so like look at the reaction to every word and like someone listening to someone else? A little bit like Gina did, like with the large language models. I think it was with like not like GPT-4 maybe.
Yeah, so
But
you mean
like,
using
can we
like
use that as like a sort of like a measure of how unpredictable like the speech produced by people is? Like,
Yeah, so you're asking, can we go even more naturalistic? Can we use actual sort of conversational data or
yeah.
even in the moment, right? Listening to what
Yeah.
people are hearing in
Yes,
conversation
I'm
with
thinking
someone.
about the data we have in my lab, but any data.
Yeah, I think there's a question about statistical power and whether or not you have in sort of these spontaneously produced data sets, right? The amount of information at very predictable words versus unpredictable words. We know that sort of naturally produced speech is relatively unpredictable. And so there will be some things to consider about the range that you're capturing in these produced speeches. But I would say that, if you're able to characterize predictability using large language models, which do relate to the neural responses that, I've captured here and others have captured elsewhere, I definitely think it is possible. It's just a matter of understanding the ranges that you can study in your spontaneously produced speech, but definitely possible, yes.
Yeah. So to have different words would not change the like N400 or the P600 or things like that. It would like, even if the word that are being heard are different, you can still like
Yeah, so one thing that's nice now about our sort of statistical methods is that we're able to sort of attribute that variability to particular variables, like the frequency that's different between these words, or how long they were produced, their duration, or sort of how closely related they are to other words in your lexicon. And we can add those in so that we can kind of try and contain some of that noise and allow us to get over sort of this complication of now these are all different words, different people, different places. So is it going to be a perfect solution? No, but it might allow us to engage, show, stronger effects of prediction in these more natural tasks, which might outweigh sort of the statistical noise that you get from not having a tight controlled experiment.
Thank you. It's very interesting. And thanks
Thank
for
you.
the nice talk. It was very
Thank you
well
very much.
presented.
Thank you.
I think that Rosa has some questions as well. Go ahead.
Yes, it's a very brief question. Congratulations, Anthony. I like it very much, your
Thank you.
presentation. Have you observed some difference between boys and girls? Because at that age used to have the language development is different. Women used to be faster.
Yeah, no, great question. We haven't split our data in those ways yet, largely because we're still collecting a lot of the samples, and a lot of the samples are a little bit uneven in terms of how many, parents report male, female, and so we actually haven't done that split yet. We've collapsed across them. One thing that I think could potentially play a role, at least in the storytime paradigm, is differences in the types of stories that kids want to engage with, or sort of their background knowledge from certain TV shows or whatnot that might sort of guide the ways in which they're able to predict. There's some classic studies in developmental literature showing, different attributions of, say, like, working with a doll versus an action figure versus an animal. And so these things are going to sort of factor in to the types of predictions that children might make. But we haven't really had the demographic split that we would need to really test hypotheses about that.
Thank you so much.
But thank you, yeah.
Anthony?
Sure.
Oh, sorry.
Yeah, sorry, another. I apologize. So one quick question. So the kids with autism in your study, and maybe I missed this, did they have significant language delays, or were they a higher functioning cohort that sort of didn't have those types of issues?
Yeah, for this population, they were a higher functioning cohort that we could recruit to come into the lab. We're still recruiting people for that task, but they've sort of showed similar language abilities as referenced by the self as the neurotypical peers that they did. So these weren't individuals with, these were individuals that were high functioning.
What would you predict would happen if you had individuals who had sort of language delays or some type of receptive difficulties with receptive speech, even if they sort of caught up at a later age? Do you think that would somehow sort of, there would be a persistent effect in processing throughout time, even if their language catches up?
Yeah, it's a great question. So I think it would be a matter of trying to characterize how processing is happening in those early developmental years, right? So if there is something sort of on the maturational or biological side about how information is being processed from the input, whether or not that's degraded, and whether or not that sort of changes across development, I think we could see that. It's possible that we could do sort of pairs, matched age groups, and see like, okay, does the processing, right, the bottom-up processing of language resemble sort of an earlier stage of development in neurotypicals versus those that have a language delay? Is the language delay just sort of a production delay, or is it sort of reflecting receptive vocabularies and receptive skills? I think that this could be a way of telling and sort of assessing differences across these populations by looking at sort of their predictive abilities in these sort of long natural discourse contexts. But I don't know of any data, no data from our lab that could speak directly to it, but it is something that could be a hypothesis easily pursued with this type of design.
Interesting. One other quick question. When does the P600 come online then?
That's a great question.
Because you didn't do the study. The studies didn't really look at the error corrections.
Mm-hmm.
I'm curious about that.
Yeah, great. That's going to be, I think, my next 5 years is going to be tracing the development of that. So I plan to do this experiment with 7 and 9-year-olds to see if, the manipulated version, to see if they start to show these P600s emerging. I will say that there are some P600-like ERP components in early studies with infants, but these are sort of really overt violations like syntactic structures or world knowledge violations. So I plan to do a task that looks at different types of anomalies, things that violate the world, things that violate syntax, things that are mispronunciations, and see if the profile of when these emerge differ. Right, these being P600s to these particular anomalies, because you could imagine that narrowing in on your particular language system or the phonological inventory that you have, or the ways in which words could change across speakers, that might take a little bit longer. But if you're certain that, a noun shouldn't go here, right, that is available really early to you, and that might evoke the P600. So it might not be the case that P600s don't exist and they don't engage in reprocessing of anomalies, but it might just be within this particular domain of misproduced speech that we're not seeing it emerging, which is also very telling.
Yeah, I just wonder, because we have childhood onset psychosis cases, and I wonder about the difference between the changes in semantic space and the predictability versus the error detection or prediction, right? And what the balance would be between the two, but clearly not.
Mm-hmm. Yeah, the other thing that's really tricky about the storytime paradigm, I ran a similar version of it, but instead of doing mispronunciations, I had syntactic errors. And so I would flip like determiners and prepositions in places. Like the books went all the way up to of ceiling. And in this natural context, for these like tiny function words that were easily reduced to natural speech, the adults did not detect them at all. They said, why did we do a 30-minute study for only 2 errors? And I said, oh, that's funny. There were 180 in there. And so when you're kind of engaged in natural context, certain things might not rise to the level of being detected. And in that study, we didn't see any P600s to the syntactic violations as we expected based on the prior literature for adults.
Interesting.
Okay, so we don't have any more questions. I really want to thank Anthony for this great talk. It was very inspiring. I really love EEG, so it was very, very interesting for me. And also, I want to thank everyone that joined today and was contributing to the discussion. The only other thing that I want to say, I hope that you join in the next talk on October 24. We will have Eric Chen. So I really hope that you can join. It has been a real pleasure to have you, and I hope to see you in the next one.
Thank you very much, everyone.
Thank you. Bye.
Thank you. Bye bye.